welcome back. Today we're going to begin a series of lectures on the CUDA programming language, which is a way to program GPUs, or graphics processing units. So let me begin with a brief history about GPUs. So we have to go back about 25 years to the mid-1990s. And so that was the time when the first generation of 3D games were appearing. And back then, computers were a lot slower. So you couldn't actually run these games very well on a computer. And so people decided that they needed to create some sort of dedicated hardware to run these games. And so that was how these graphics processing units came about, as like co-processors for the CPU to run these games. Right? So you see on the right over here, we have this Voodoo 3 card, which was a very popular card back in those days. Right? And that could let you play these games like, so the game that you see above, this is called Doom, right? So this is like one of the first, it's either the first or second Doom. And, incredibly, Doom is still around nowadays, right? So they just released a new version of Doom. So it's been like, 25 years almost. But back then, this Doom was quite a revolution. And so the graphics was considered like, really amazing back then. Okay, so now you have these GPUs. And the thing about the GPUs is that, first of all, they need to produce a lot of output. So they need to have very high throughput. And the reason is that, if you look at one of these screens, for example, for Doom, we have, let's say, 640 pixels by 480 pixels. Right? So, of course, nowadays, that's a very low resolution. But back then, that was a lot of work that you had to do just to render this one frame. And you had to do that like 30 times a second. Okay, so therefore, every second you need to compute like millions of pixels. But the nice thing about these workloads, these graphical workloads, is that there's a lot of parallelism in the workload, because you can basically compute each pixel independently, right? Like so you can assign like a single thread to compute a pixel, and then you can assign a different thread to compute the next pixel, right? So if on a screen you have 100,000 pixels, then you can actually run 100,000 threads to produce that screen. Okay, so now eventually these games got to be better and better looking, right? So to improve the graphics quality, what you needed to do was actually make every pixel somehow look nicer, right? So to make it look nicer, people ran these little programs for every pixel. So these programs were called pixel shaders. Okay, so they improve the quality of each pixel. And so therefore for the GPUs, in addition to having high throughput, there was also this requirement that you could individually program these threads, right? So the threads are computing the pixels, and these pixels need to run these little pixel shader programs. Okay, so therefore you had this architecture being developed, this GPU architecture, which had was capable of a very large amount of parallelism, and furthermore, these parallel threads are programmable because you have to run the pixel shaders. Okay, so then people pretty soon they started realizing that you can use GPUs not just to play games, but you can use them for other types of parallel workloads. Okay, so for example, if you need to do some sort of simulation, right, like a fluid dynamics simulation, or if you need to like render an MRI image or something, right? So all of these workloads have the property that they have a lot of parallelism. And you need some general purpose way of programming them. So people, and then the GPUs actually have a great deal of computational power. So people started adopting the GPUs for these other types of workloads. Okay, so that was the start of something called GPGPU, which was general purpose GPU, right? So it's not just about playing games anymore. It's about like general purpose computations. And this GPGPU concept became so popular that eventually, around 2006, NVIDIA, which is one of the top makers of GPUs, both back then and also today, they introduced a way for, they introduced a Tesla card, which was a GPU that was fully programmable. So before then, when people were using these GPUs to do general purpose applications, you had to write these programs in a very strange way, because the GPU itself was actually designed for games, right? So if you want the GPU to solve some other problem, you have to somehow change your problem so that it looks like you're actually doing some sort of graphical computation, right? So you could be computing something unrelated to graphics, but in order to run your code on the GPU, you have to somehow convert it to something that looks like computer graphics. Okay, so that was before 2006, and after 2006, NVIDIA decided that so many people were using GPUs for general purpose computations that they might as well make it so that GPUs can be programmed in a much simpler way to do these general purpose computations. Okay, and in fact, not only did they introduce this Tesla card, right, which was easy to use for other purposes, they also introduced the CUDA language, right? So the CUDA language makes it much easier for you to write general purpose code on GPUs. Okay, so since about 2006, GPUs have really taken off, and now they're basically an essential part of modern computing. Okay, there are so many things that need GPUs, because if we simply relied on CPUs, we wouldn't have enough computational power for many tasks that are important nowadays. For example, machine learning, right? If we had to run all of our machine learning workloads on CPUs, then there's basically no way that we can scale to the size of these machine learning models that we have nowadays, just because GPUs are so much faster than CPUs, right? So now so nowadays GPUs are included in many other types of computers, right? So for example, you could have a very large supercomputer, which not only has thousands of CPUs, it also has thousands and thousands of GPUs. Okay, and because there's so much usage of GPUs, and because they're so efficient for many problems, there's also a large amount of research on GPUs. Even today, it's an active research area. Okay, so GPUs basically have several teraflops of performance. Okay, so nowadays you can buy a GPU card which has 10 to 20 teraflops of performance on a single GPU. Okay, so I think I mentioned this, but if you look at the fastest supercomputer in the world in the year 2000, okay, so that computer, that supercomputer had about 10 teraflops of computational power. Okay, so nowadays you can buy a GPU for like I don't know, $500. Okay, and that's got the same power as that supercomputer back then. Okay, another nice thing about GPUs is that they're more energy efficient than CPUs. Okay, so GPUs do take a lot of power, but because they can do so much computation, then the amount of power you're using per unit of computation is better for GPUs than for CPUs. Okay, and power usage is nowadays like more and more it's becoming an important consideration. Okay, so what is the major difference between CPUs and GPUs? So it's actually kind of a philosophical difference. Okay, so CPUs, if you want to do something fast, let's say you have many things to do, okay? So one way that you can do all of these things fast is you can do each individual thing very quickly, okay? So that's basically the CPU philosophy, is that if you want to solve a problem fast, a bunch of problems fast, you're going to solve each individual problem fast, okay? Now the GPU philosophy is different, okay? It's saying that if you want to do many things quickly, right, then what's going to happen is, well, the GPU might actually take a long time to do each thing, okay? However, it's going to do many things simultaneously, okay? It's going to have a high degree of parallelism. And in fact, yeah, so if we look at this diagram on the right over here, right? So the CPU, if you have a bunch of these tasks, which are these little ovals here, right? The CPU is pretty fast on each task, okay? But the CPU only has a few cores, right? So nowadays you might get a very high-end CPU might have, let's say, a dozen or 24 cores, okay? But not more than that, okay? And so in each given amount of time, you can only solve a limited number of problems, even though you're solving each problem quickly, Right? Now the GPU, if you look at each task, the GPU might actually be slower on each task. Okay. However, the GPU is going to have so many processors. Okay, it can have thousands of processors that overall, in each unit of time, you can solve many more problems on the GPU than the CPU. Okay, so this is basically so these two philosophies are the latency the latency versus throughput philosophy of parallel computing. Okay, so CPUs try to minimize latency for each computation, tries to make every computation fast, whereas GPUs try to maximize throughput. Right, they only care how many things you do per unit of time. They don't care how much time it takes to do each individual piece of work. Okay, yeah. So the CPUs are exemplified by the multi-core processors, and they just have a few cores. Okay, and the GPUs are these throughput-oriented processors, and they have many cores. Okay, so what makes it so that the GPUs can have so much parallelism, right? Why is it that we can build GPUs with thousands of cores, but for the CPUs we only have a few dozen cores, right? And the reason is that remember that the CPU wants to minimize latency for every single task, right? And so it wants to compute very quickly, and to do that, it needs a very complicated architecture. Okay, so this architecture includes many things to make each operation run as fast as possible. So, for example, it could do things like so on the right here, I have this diagram showing some features of a typical CPU. So it might do things like, memory prefetching, or a lot of fancy branch prediction, or some out of order operations, right? So so there's a lot happening in a CPU. Oh, and it's got a big cache, right? Yeah, and all of those fancy features on the CPU, they make your code run faster, but they also take a lot of space physically on the chip. Okay, because chips are made from wires, and wires can only get so small. So in order to build one of these CPUs, right, the CPU itself, the CPU core, is actually quite large. Now the GPU, okay, so the GPU doesn't try to make each task run fast. Okay, so therefore the GPU doesn't really need all of these complicated features that the CPU has, right? It doesn't really do out of order computation or branch prediction or all of this other stuff, right? So and it doesn't have a big data cache. Okay, the GPU, all it wants to do is compute. Okay, so basically each GPU core is much simpler than a CPU core. It just has a few components of the core that you can fetch the instructions, right? You can compute the instructions, and then you need registers. Okay, so it does away with all of these other complicated CPU features, and so therefore each GPU core can be made much smaller than a CPU core. Okay, and because you can make these GPU cores smaller, right, then you can fit more of them in the same area. Okay, so so in the same area that you can fit a few dozen CPU cores, you can fit thousands of GPU cores. Okay, so for example, one of the newer GPUs are these Tesla P100 GPUs. Okay, or sorry, the Pascal architecture. Okay, so the P100s they have these. So now, if you look at this diagram over here, okay, each of these little green squares is actually a core. Okay, so this is like a block diagram for a GPU. And now these cores are sort of organized into these little units that you can kind of see, right? So these units are called SMs, or streaming multiprocessors. Okay, now for the Pascal, the P100, each of these SMs actually has 64 cores in them. Okay, and the entire GPU card has 56 of these SMs. Okay, so if you multiply 56 by 64, you get that this entire GPU has 3,584 cores. Okay, and all of these cores can run simultaneously. Right? And by doing that, you actually get 11 teraflops of performance from this card. Okay. Now, in addition to this, the GPU also has very high memory bandwidth. Okay, so it has up to 720 gigabytes per second of memory bandwidth, and that's much higher than what you can achieve with a CPU. Right? However, the GPU does not have a lot of memory. It only has, let's say, 16 gigabytes of memory. Okay, so that's a lot less than what you can put on a CPU. Okay, so that's usually one of the weaknesses of GPU is the limited memory, right? Because yeah. Okay, now in contrast, if you compare like one of these pretty high-end GPUs to a high-end CPU, right, like this Intel Xeon over here, right? So this has 24 cores. Each of them can do hyperthreading, so you can actually run 48 threads simultaneously. But altogether, you're only getting about 3 teraflops of performance on this very high-end Xeon. Okay, so then now that we see GPUs are much faster than CPUs, right? So the question is, all right, so let's just forget about CPUs. Let's just use GPUs for everything. Okay, but unfortunately we can't do that. Okay, so GPUs are even though we say that they're general purpose, right? The GPUs are still optimized for certain types of workloads, and there are other types of workloads that CPUs perform better on. Okay, so now if you just look at the raw computational performance, right, how many teraflops a GPU or a CPU has, right, then oftentimes you can see that GPUs have, let's say, 10 times as many teraflops, can do 10 times as many teraflops as a CPU. And so if you have the right type of problem, then you can solve it, at least 10 times faster on the GPU compared to the CPU. Okay, and plus you can save some energy because they're more energy efficient. And so because of this, there are many supercomputers that use many GPUs. Okay, so this Titan supercomputer over here, it has a lot of CPUs, but it also has like about 20,000 GPU cards. Okay, and these GPUs actually provide most of the computational power of this supercomputer. Okay, but again, these GPUs are limited in the types of tasks that they're optimized for. Okay, so the GPUs work best for what are called data parallel tasks. Okay, which I'll show you. And the reason that they work well for these data parallel tasks is because of how the GPU architecture is designed. Okay, so the GPU, in order to achieve this high parallelism, they're based on the SIMD architecture. So remember that SIMD stands for single instruction, multiple data. Okay, so there's basically one instruction fetch and decode unit, right? So that's gonna so that unit grabs an instruction and then it assigns the same instruction to many cores, to let's say 32 cores. Okay, now these 32 cores are going to do that instruction on different pieces of data. However, they're all doing the same instruction. So now the problem becomes that what if you want the cores to do different instructions? Okay, so for example, if you have a code with lots of branching, okay, so one branch is going to add, the other branch subtracts, but then that's not SIMD anymore, right? Because it's not a single instruction, right? It's different instructions. So in that case, those workloads don't work so well on GPUs. Okay, so GPUs work well for these data parallel tasks where you just simply want to apply, like say, one operation, the same operation on many pieces of data. Okay. However, if you have irregular workloads, then it becomes problematic to run those on GPUs. And also, GPUs have much fewer ways to synchronize between the threads than CPUs. Okay, so if you have a code with lots of synchronization, then oftentimes it's not even possible to run that type of code on the GPU. Okay, not only is it going to be slow, it's sometimes just not. It's impossible to run the code. Okay, so what are these data parallel tasks? Okay, so basically the idea for data parallelism is that we're going to apply the same operation on multiple data items, right? So we're parallelizing across the data. Okay, so now it turns out that there are many problems which are data parallel, right? So of course there are problems which are not data parallel, which are parallel but not data parallel. Okay, but there are also many important parallel problems which are data parallel. So for example, suppose you want to add two vectors. Okay, so we have an A vector here and a B vector, and all we want to do is for each component of these two vectors, we just want to add them, right? Okay, so that's a perfectly data parallel task because we're just doing the same operation, addition, right, on many pieces of data, right? So the first component of A and B, right, we do the addition, right? The second component of A and B, we also do an addition. right? So now imagine that you had a bunch of processors, and if you assign one processor per per component, right, then all the processors would be doing the same instruction on multiple pieces of data. Okay, so that's a pretty simple example, but if you think about it, many linear algebra operations actually are quite similar to just vector addition, right? So if you do something more complicated, like a matrix vector multiplication, okay, so that's actually used in many, many tasks, right? If you can do matrix vector multiplication fast, you can actually solve many problems fast. Okay, but matrix vector multiplication is, has a very similar computational pattern to vector addition, right? Because you just take your matrix and you go through a row, and then you do the dot product with a column, right? So the dot product is simply that you for every component you do a multiplication, and then in the end you have to add all those up. Okay, so that's a very similar sort of data access pattern and computational pattern as vector addition. And so most dense linear algebra operations are data parallel. Okay, computer graphics, right? So that was the original purpose of GPUs, was computer graphics, and those are often quite data parallel because again, you have to, like, let's say you have to produce a picture of some sort. Okay, so every pixel on this picture, right, it's produced using basically the same process, right? Whether you're doing something like a game or even something more complicated like ray tracing, right? You're still doing more or less the same process for every pixel. So therefore, that's also we're doing the same operations on multiple data items. Okay, there are many other tasks like some sort of data analysis, right? If you try to do like a frequency decomposition, right? If you do convolutions, right? So many types of simulations are data parallel, and also a lot of machine learning tasks are data parallel, right? Like deep learning is one of the best examples because deep learning depends heavily on GPUs. Without GPUs, we probably couldn't do large-scale deep learning. But deep learning basically turns out to be something like dense linear algebra. And so GPUs are like an excellent architecture for that. Okay, so now let's look at an example of how we do a computation on a GPU. Okay, so we're going to go back to this vector addition example. So let's first start with a sequential program for vector addition. Okay, so this is very simple. So if your vector has n items, right, we're just going to iterate through all of the items, all the indices, right, and then add the item from A and the item from B and store that into C. Okay, so it's a sequential process and it takes you n steps. Now, if you do this on a GPU, what's going to happen is instead of so for the sequential computation, you had one thread which processed all of the elements, right? Now on the GPU, we're actually going to have each thread process only one element. Okay, so for every element of the output, so if your n is like 1,000, right, we're going to launch 1,000 threads. Each thread is just going to produce one of these outputs C. Okay, so that's sort of illustrated over here, right? So you don't need to worry too much about this notation right now. But basically, what it's saying is that so here somehow we're computing the so the ith thread over here. Okay, is going to process the ith data item. So then here we would have 256 threads. And in fact, you can have a lot more than 256. So for GPU computation, you can very well have millions and millions, many millions of threads. Okay. Now we're going to talk later about so you have millions of threads, but you don't have millions of processors, right? Like we said, the Pascal GPU has a few thousand processors, and so we're not going to be running all of these millions of threads simultaneously. Right, that would also involve a lot of overhead to keep track of all of these threads. Okay, so that's just not feasible. Okay, however, we do create millions of threads, and then later on I'll tell you how these threads are actually executed on just a few thousand cores. Okay, but in principle we create millions of threads, right? And somehow the GPU hardware, so I'll tell you more later, is designed so that we can actually make use of all of these threads. and there's very little overhead to switching between the threads. So this is another difference with CPUs. Okay, with CPUs, whenever you switch between a thread, that's actually a fairly expensive operation, right? So you don't want to be switching between different threads all the time, because you would be wasting basically all your time just doing the thread switching. Now on GPUs, the hardware is designed so that there's almost no overhead whatsoever to switching between the threads. Okay, and so that's why it's possible to have millions of threads. Okay, so now we're going to be talking about a language called CUDA, and CUDA is basically the sort of de facto way that you program GPUs nowadays, at least NVIDIA GPUs, which are the most popular GPUs. Okay, so CUDA stands for Compute Unified Device Architecture, and it basically allows you to use a GPU as a coprocessor for CPU, right? So it lets the GPU help the CPU do some sort of computation. Okay, so yeah, so the way this works is that so CUDA is based on C, and so so to write a CUDA program, you basically write something which looks basically like a C program, right? Except for it's got these CUDA extensions. Okay, and then you're going to use the CUDA compiler, the NVIDIA CUDA compiler, right? And so that's going to produce code that can run both on your CPU and your GPU, because your CPU and GPU have to work together in order to run the CUDA code. Okay, so basically, these CUDA programs that use the GPU, right? They still start on the CPU. Okay, and then the CPU eventually passes control to the GPU. Okay, but the CPU and the GPU have to work together. Yeah, so this is a very popular way to program these GPUs, the NVIDIA GPUs, and NVIDIA provides lots of nice tools for using CUDA, right? So they have a compiler, they have like debuggers, they have profilers to tell you like, where the bottlenecks in your code are, and so on. Okay, now besides CUDA, there are other ways to program GPUs. For example, there's an open standard called OpenCL, right? And there's also something called OpenCC, OpenACC. So OpenCL is basically, it's quite similar to CUDA, okay? So if you know CUDA, then you can learn OpenCL like in an afternoon. So it's very similar to CUDA, both conceptually and syntactically and so on. But the advantage of OpenCL is that it's more portable than CUDA. So for example, OpenCL also works on the AMD GPUs, okay? And then, in fact, you can take the same OpenCL source code and you can compile it even for different processor architectures, right? So you can compile it for the GPUs, but you can also compile it for CPUs or FPGAs, okay? Now, the price that you pay for this portability is that it performs a bit slower than CUDA, right? Not too much slower. So maybe like 20% slower for many tasks. Okay, so it's not too bad, and you gain a lot of portability. But we're not going to talk about OpenCL because, as I said, we're going to focus on CUDA. But once you know CUDA, you can pick up OpenCL very easily. Okay, there's also this thing called OpenACC, and this is kind of similar to OpenMP in the sense that you can write GPU code using these directives. Okay, so remember that in OpenMP, the way we achieved parallelism was using these like pragma OMP statements, right? That create threads for us and then that divide up the parallel work for us. Okay, so then OpenACC is similar. You use these directives, and then that tells the compiler how you want the parallelism to go, and then the compiler will take care of this process for you. Okay, now OpenACC is the performance is not at the same level as CUDA, right? So it's actually quite a bit slower than CUDA. However, it's easy. It's quite easy to use because as you saw with OpenMP, right? That's a very easy thing to use. Whereas CUDA is, there's a lot to think about when you write a CUDA program. Okay, so that's why we're spending a number of different lectures on CUDA. Okay, so then now let's talk about the steps to writing a CUDA program. Okay, so you basically to write a CUDA program, you write a C program, and then you add some CUDA annotations. Okay, and then you compile this with this MVCC, right, the NVIDIA CUDA compiler, and then you can run this. Okay, and the way you run this, the way you run CUDA programs is that you're going to start the CUDA program on the CPU. Okay, so the CPU is called the host. Okay, and the host is going to do some like sort of initialization parts for you, and it's going to run some serial code. Okay, and then eventually you get to the parallel part, and then you want to run that on the GPU. And to do that, the first thing is you need to allocate some memory on the GPU, right? And usually we call the GPU the device. Okay, so the host is the CPU, and the device is the GPU. Okay, so we allocate some memory on the GPU, and then we transfer some data, the data that you want to compute with, onto the GPU. Okay, and then you have to tell the GPU how many threads you want. Right, so this depends on like the workload that you're running. Okay, but you specify the number of threads, and then you call the GPU code, and the GPU code is called a kernel. Okay. Yeah, and then eventually this kernel finishes the GPU computation, and then it can return control back to the CPU. Okay, and then the CPU can do some more computation, but then it can invoke the GPU on another kernel. Okay, so we go back and forth between the GPU and the CPU. So that's kind of this process on the right over here, where the single line here is like a single CPU thread, and then you start up a bunch of these GPU threads, right? And when they finish, you go back to the CPU, and then go to the GPU, and so on. Okay, so I'm going to talk a bit about the syntax of these CUDA functions. Okay, so we have different types of functions in CUDA. So for example, if you have a so when you declare a function, you need to prefix it with this label here. Okay, so for example, the first label is double underscore. Okay, so there are two underscores here, and then device, and then two more underscores. Okay, so if you specify that if you label a function this way, then what this means is that this function is executed on the device, right? So it's executed on the GPU, and it's called from the GPU. Okay, so that's sort of after you start the GPU program, right? If you need to call the subroutine from the GPU, then that's you're going to label it with device. Okay, if you label your function with global, right, then this is being executed on the GPU, but it's called from the CPU. Okay, so for example, to start your GPU program, right, you need a global function on the GPU that the CPU can call. Okay, and then you can have this these host functions, so double underscore host, double underscore, and this is like a CPU function that is also called from the CPU. Okay, so we have functions to allocate memory on the GPU. So so for example, there's this function called CUDA malloc, right? So here you give a pointer to where you want the memory to get back the location for the memory that is allocated, and then you specify the size for how much memory you need. And we said that to start a CUDA program, you need to transfer some data from the CPU to the GPU. Okay, so now suppose suppose x is some data on the CPU. Okay, and let's let dx, right, device x, be a pointer to the device memory. Okay, so that so dx was somehow created by this CUDA malloc. Right. Now, to transfer data from the CPU to the GPU, right, then we can call this function CUDA memcopy. Okay, so then here you give the device address, the host address, the size of what you're transferring, and since you're transferring from the CPU to the GPU, you have to write this thing over here. And then also, eventually the GPU finishes, right? So maybe you want to get the output back from the GPU. So then, again, you can use CUDA memcopy, but you use it in the other direction. Okay, so now you're copying to the CPU from the GPU, right? And you need to specify that it's in that direction. Okay, so now for the CUDA functions, when you call a, so the functions are called kernels. Okay, so GPU functions are referred to as kernels. So when you run a kernel, so these things are always going to be parallel, right? You would never want to run just a single thread on a GPU. And so you have to say how many threads you want in the kernel. Okay. Now, you don't just give a single number for the number of threads. Okay. So if you want 1,000 threads, let's say, okay. So your 1,000 threads actually have to be grouped hierarchically. Okay. You first group these threads into things called blocks, thread blocks. Okay. And then you have to say how many blocks you want and how many threads per block you want. Okay, so for example, in this picture here, right, we're going to create n blocks. Okay, so n can be like a large number. It can be like 1,000 or 1,000,000 even. Okay, and then within each block, we're going to specify how many threads you want. Okay, so here you have 256 threads. So usually you're not going to have very, very many threads, right? So in fact, there's a limit to how many threads you can put into a block, which is usually something like maybe a few hundred or maybe 1,000. Okay, but you can have many, many blocks. Okay, so now that you specify how you want to call a function, right, then in order to call that function from the CPU, right, what you say is, suppose you want n threads total, okay, and then suppose you want to divide these threads between t blocks, okay, so then you have basically n divided by t thread blocks, right, and we take the ceiling of this number. Okay, so now the way you call the kernel function is you use this notation. Okay, kernel function, and then you have to use 3 less than signs. Okay, and then you have to give the number of blocks, the number of threads per block, right, and then 3 greater than signs, and then the arguments. Okay, and so this way we're guaranteed to have at least n threads, right, because the number of threads is like the number of blocks times the number of threads per block. Okay, so now let's see how we can use this to in a simple example. So let's go back to this vector addition example. Okay, so yeah, so all we want to do is we initially have 2 vectors a and b sitting on the CPU. Okay, and we want to add them up. Right, we want to use the GPU to add them up. Okay, so what we do is okay, so we have these pointers for A, B, and C. So these pointers are going to be pointing to GPU memory eventually. Okay. So the first thing we're going to do is we need to allocate some memory on the GPU. Right. So initially the A and B vectors are sitting on the CPU. Okay. So to get the GPU to add them, we need to transfer the A and B vectors to the GPU. So the first thing is to allocate memory on the GPU. Okay. So we're going to allocate this much memory. Right. So this is we're going to call CUDA malloc. And the size we're gonna allocate is let's suppose we have n numbers in the vectors. Okay, so we're gonna allocate this many bytes on the GPU. Okay, and then next we're gonna take the data from the CPU, right, and then transfer it over to the GPU at this pointer location, right? And then we do the same thing for B, right? You malloc B, you CUDA malloc B, and then you CUDA mem copy B to the GPU. And then you malloc some space on the GPU to store the output, right, in C. Okay, and then next we're going to call a GPU function to actually do this addition. Okay, so this is the GPU kernel that is the actual addition kernel. Okay, and now here notice that we need when you call it, we need to specify the number of thread blocks, right, and the number of threads per block. Okay, so here we decided somehow that we want 256 threads per block. Okay, so in fact, I'll talk to you later about how we decide how many threads you want per block. Okay, but right now, let's go for 256. So in that case, since we have n items in the vector, right, and we plan to assign 1 thread per item. Okay, each thread is just going to compute the addition at 1 coordinate of the vector, and so therefore we need n threads in total, and so the number of thread blocks is going to be n divided by 256. Okay, and then you're going to give these some arguments, which are these locations where the data is being stored. Okay, so we'll get to the kernel later, but after you do this computation, right, then eventually the answer is going to end up in this DC location. Okay, so this is some memory on the GPU that's storing the sum of the vectors. So we want to get that vector back. So we're going to call this CUDA mem copy from the GPU back to the CPU. right? And then you free your code. You free your the memory on the GPU, right? Okay, so all of this is a CPU program. CPU function. Okay, this is a CPU function, and so when you call it, right, we're gonna have our main function, right, and we call this function, and this is gonna run on the CPU first of all. Okay, so the CPU initializes all the data, and then the CPU calls the GPU kernel. Okay, now finally, let's look at the GPU kernel. So first of all, this is the GPU kernel is being called from the CPU. So therefore, we have to label this kernel a global function. Okay, and so this is our kernel. It's actually very simple. So each thread, okay, is when you call this kernel, you're going to start many threads. Okay, in fact, you're going to start at least n threads. Okay, now each thread is going to have its own ID. Okay, and also the thread is going to belong to a particular thread block. So remember that you start a number of thread blocks here. Let's say you start 100 thread blocks. Okay, in that case, each thread is going to have a block ID from 0 to 99. Okay, and then each block here has 256 threads. So therefore, the thread also has an ID within its block, which is a number from 0 to 255. Okay, so yeah, so the thread has two ways of identifying itself. First, which block is it in? And second, which ID is it within that block? Okay, now we do this computation over here. So I think later I'm gonna so I'll talk more about what this computation here is doing later. Okay, but anyways, somehow you use the ID of the thread, right? Its block ID and its thread ID to compute some index into this array. Okay, and then we just the thread is just responsible for the addition at that single index. Okay, so it just takes A of I and adds it to B of I, and then stores it in C of I. Okay, now the thread is going to check that this index that it computed, this needs to be less than the size of the array. Okay, because it's possible that a few of these indices can actually be larger than the size of the array. Okay, so as long as we are within the array bounds, we're going to do the addition. Okay, so now we started a lot of threads over here, right? Each of those threads computed one index and did one addition and stored that result somewhere in C. Okay, so now it's going to turn out that the way we compute these indices, right, we're going to end up for every index from 0 to n minus 1. Okay, so for every component of that vector, okay, we're guaranteed that there's at least one, actually exactly one thread which is going to process that component. Okay, so that means that for every component of A and B, we had a thread to add them and to store that result in C. And so that's why the result in C, after all of the threads, after all the threads that you start here, right? You could start many threads, right? After all of them finish, right? Then we have the correct answer in C. Okay, so now this kernel is only gonna return after all the threads that we started have finished the kernel. And so at that point, we know that the correct answer is in C. And so that's why we can call this CUDA memcopy here to get the answer back from the GPU. Okay, so now let's talk a bit more about this, about the fact that threads, if you want, let's say 10,000 threads, okay, you don't just start 10,000 threads, you have to group the threads into blocks, right? And you have to say how large each block is. Okay, so so the way the threads are organized is that all of the threads are going to run the same code. Okay, so if we go back to this kernel here, then you see that here every thread is going to run the same code. Okay, however, they're going to work on different data items. Okay, because every thread has a different either it's got a different thread ID or different block ID. Right? Or actually, the way to say this is that if you look at the combination of the block ID and the thread ID, okay, so if you look at, let's say, if you take any thread and you look at its block ID.x and the thread ID.x, oops, let's see, ID.x, right? If you look at two different threads, right, then they're going to have different ones of these pairs. Okay, so even if two threads have the same block ID because they're in the thread block, right? In that case, they would have different thread IDs, right? And if they have the same thread ID, right, then they have to be in different blocks. Okay, so therefore the threads can are all. It's going to turn out that the threads are all going to work on different indices. Okay, but they all run the same code. So this is exactly this SIMD concept that we talked about, right? They run the same instructions, right? Because every thread is first of all going to do this addition, this multiplication, these memory accesses, and so on. So they all run exactly the same code, but they do operations on different data items. Okay. Now I should say that in CUDA, conceptually it's supposed to be a SIMD architecture, right? So we want the threads to do the same instruction all the time. Okay. But in practice, if you completely limit yourself to that type of program, right, then that's a big limitation, right? There are many programs that you cannot write in that fashion. So therefore, in practice, CUDA can run threads where they do different instructions. Okay, but there's a big performance penalty to doing that. Okay, so that's called thread divergence. So I'm going to talk more about that in a later lecture. Okay, so conceptually, you should think about the threads as running the same instruction. Okay, but in practice, they can run different instructions, but then you have to pay a performance penalty. Okay, so the threads. All right. So getting back to this, the threads are organized into two levels. So now we start a bunch of thread blocks, right? And if you take that collection of thread blocks, okay, so then that is called the grid. So the GPU when you run a GPU kernel, you first create a grid of thread blocks. Okay. Now each thread block has to have the same number of threads. Okay, and it turns out that okay, so then about this grid, right? So here we see a grid, right? So we see a grid of n thread blocks. Okay, now it turns out now here is a one-dimensional grid, right? Because the thread blocks, right? Their ID is just it's just a number. Okay, so it's a 1D thing. Okay, now you could actually have a 2D grid. Okay, in that case, we have a bunch of blocks. And each block has two coordinates. Okay, so maybe you're a block in the second row, fourth column. Okay, so right now we just have, let's say we have the fourth block. Okay, but if you have a 2D grid, then you can have a block in the second row, fourth column of all the blocks, right? And CUDA even supports 3D thread blocks. Okay, so basically, the reason CUDA supports this stuff is because oftentimes the types of programs that you run are some sort of simulation code. Okay, and the simulations are usually taking place in either 1D, 2D, or 3D. Okay, so you could have higher dimensional simulations, and CUDA does not have like hardware support for arbitrary dimensions of grids and blocks. Okay, but it at least supports these common ones. Okay, so all right, so I'm still not going to talk to you about why we have these both a grid of thread blocks and why we have both blocks and individual threads. Okay, so I'll get to that later, but just yeah. Okay, so now how do we we start this grid of threads. Right? So how do we map the individual threads onto the data that we care about? Okay, so this of course depends on the problem that you're solving. Okay, but I'll do an example with the vector addition problem. Okay, so here, yeah, so when you start the kernel, right, every thread is going to get a unique block number, right, this block ID, okay, and thread ID within that block. Okay, so this is what I said earlier. Okay, where was it? Okay, so if you look at different threads, okay, so then this pair here is going to be unique. Okay, you could have the same thread block, but then the ID is going to be different. Or if the ID is the same, then the block is going to be different. Okay, so therefore, you can uniquely identify a thread by this by these two parameters here. Okay. Now, also, the number of threads in a block. Okay, this is given. So by the way, these are these are sort of values which are defined by CUDA. Okay, so for example, you can't create your own variable called with this name. Okay, so this is a special special name for a CUDA variable. And so there's another named variable, which is this block dimension. Okay, so block dimension is like how many threads you have per block. Okay, so when you call a CUDA function, right, you specify how many threads you want per block, right? This t here. Okay, so this block dimension is exactly this t here. Okay, now going back to our vector addition example, what we want to make sure is that every item in the vector, right, in the two vectors, is processed by some thread, right? Because we want, let's see. So, right, so you want to make sure, so if you want to add A and B, right, if you want to make sure you don't miss any of the coordinates of A and B, you have to make sure that for every index, right, from 0 to n-1, you must have at least one thread that's processing that index. Okay, so the way you ensure that is using this formula over here. Okay, so this formula, this is specially designed for this vector addition example. If you have a different problem, right, then you might want to use a different formula. Okay, but here at least let's take a look at what this formula is saying, right? So this formula is saying that for each thread, we're going to take the sort of the name of that thread, right, and then we're going to do this computation. Okay. And then now the claim is that what this computation achieves is, well, let's get some concrete numbers here just to make things easier. Okay, so suppose here that we have thread blocks, and let's say you have 100 thread blocks. Okay, right? So oops. So here we're gonna have 99. Okay, right? And then we have 256 threads per block. Okay. So then what's going to happen is this block ID thing, right? This block ID dot x. Okay. So then this is going to be a number between 0 to 99. Okay. Right. And then this block dimension here, block dim dot x. Oops. Write that a bit nicer. Okay. Okay. This is how many threads are in each block, right? That's 256, right? We have 256. Okay, and then the thread ID dot x is going to be a number between 0 to 255 because it's the ID of a thread within its thread block. Okay. Now, now the fact that you have 100 of these blocks. Okay, so remember the number of blocks we have is equal to the number of items we have divided by the thread size. Divided by the number of threads per block. Okay, so basically here we had 25,600. So we had let me rewrite this. So we had n equals. So we had vectors with 25,600 elements in them. Okay, and then you divided this into 100 blocks of 256 threads each. Okay, right, so that ensures that we have the same number of threads as we have elements. So we can have one thread process each element. Okay, now we need to make sure that every thread processes a different element. Okay, because we have the same number of threads as elements. So if we want to process all the elements, we better not have two threads process the same element. Okay, now I claim that this formula, right, this formula over here is going to produce a number between 0 to the to n-1, to little n-1, okay, to 25,000, what is it, 599. Okay, and you can check that because block ID here, right, block ID here is a number between 0 to 99, right, times the block dimension, right, this is this here is 256 over here, right, the thread ID is going to be a number from 0 to 255. So now you can check that as you consider all possible block IDs between 0 to 99, okay, and all possible thread IDs between 0 to 255, right, then when you plug these things into this formula here, you're going to get all possible numbers between 0 to 25,599. Okay, so you can just check that, right? So basically what this formula says is that it's going to map each thread, which is uniquely identified by these two numbers here. It's going to map each thread to a different vector element between 0 to 25,599. Okay? Yeah. So for example, if you take the 23rd thread, right, in block 3, right, we are going to map that to element 791. Okay? So you can check that every element in the vector from 0 to n-1, okay, was assigned some thread. Okay, for every number from 0 to n-1, we can find some settings for these two numbers between these ranges, within this range, right? So that this formula equals the number. Okay, right? And also you can check that since these values are unique for every thread, right? Then every thread is going to process a different element. Okay, so if you put these two together, we see that every element in the vector is processed by some thread, by one of these threads that we started up here. Okay, so we started 100 thread blocks with 256 threads each. Okay. Now, of course, this is not the only possible mapping. Okay, so we use this mapping because we wanted to have one thread process just one element. Now, if you have one thread process, let's say several elements, okay, so sometimes you might want to do that. Okay, then you would use different mappings to achieve that. Okay, now you usually will not have one thread process many elements. Okay, so for example, you definitely do not want to have one thread process all 25,000 elements. Okay, because then you don't have any parallelism. So usually you want each thread just to process a few elements. Okay. Now yeah, I guess I'll just mention this now, which is that you see that each of these threads is, let's go back here, right? Each of these threads is doing something very simple, right? It's just adding two numbers, right? Now, you might wonder, like, isn't there some overhead to creating this thread and to like sort of allocating all the resources for this thread and so on, right? And so you have to pay that overhead to work with this thread. And then all you ask the thread to do is to do this like super simple computation, right? So aren't you like wasting a lot of time on allocating these threads? Okay, now the thing is that, again, the GPU architecture is designed so that allocating the threads and like switching between the threads and scheduling the threads, all of these operations are very, very cheap. Okay, so almost like no overhead whatsoever. Okay, so it's almost free to create threads. And so therefore, even though we're asking each thread just to do such a simple operation, right? Because we almost have no overhead for creating that thread, then we are actually not wasting much of our resources. Yeah, so in case you were wondering, and I'll talk more about this later, okay? Why is it, what's so special about the GPU architecture that lets it work with threads in such a cheap way? Okay, so now this here is a 1D thread mapping, right? So we have a one-dimensional set of thread blocks, right? Because all the thread blocks are just numbers. Okay, so it's 1D. Okay, and now within each thread block, right, the threads also are just identified by numbers. So it's also a 1D organization of the threads within the thread block. Okay. Now, in fact, CUDA lets you work with higher dimensional grids and thread blocks. Okay, so what that means is, for example, if we have a 2D grid, right, then each block would be identified by two numbers. Okay, right, like this. Okay, and then each of these thread blocks in here, right, so in the previous example, it was just a 1D thing, but you can also make the thread block a 2D thing. Okay, so if it's a 2D thread block, then each thread within the thread block would be identified by two numbers, right? Like thread 10, thread 20, and so on. Okay. Now, in that, and you can also make this 3D, right? And so 2D would be useful for things like if you're processing matrices, right? Then it's kind of natural to create a 2D grid or thread block to represent that, okay? Or computer graphics, right? Because graphics is usually like we're working in 2D. Okay. Now for 3D, right, you might be working with like some sort of 3D data, right? Or maybe you're working with 2D, but you have a time component, like you have a video or something. Okay, so then that would make sense for 3D. Okay, so this is basically for convenience. Okay, the fact that we can have these multi-dimensional thread blocks and grids, it's sort of mostly there to make your programming life easier. Okay, strictly speaking, if you wanted to process 2D data, right, you could actually use like a 1D representation. Okay, it might be a bit less efficient, but you can definitely work with it. Just to make things as natural as possible, right? CUDA provides this 2D and 3D abstraction. Okay, but nothing beyond that again. Okay. Yeah. So. Oh, right. And the dimensions of the grid and the thread blocks do not have to be equal. Okay, meaning that, for example, you could have a 2D grid, but within the 2D grid, all the thread blocks are one-dimensional. Okay, or some other combination. Okay. Now, if you have a multi-dimensional thread block, right, or a grid, right? Well, first of all, we need to know how big those grids or the thread blocks are. Okay. So remember that for a 1D 1D thread block, right? We have this built-in parameter here, blockdim dot. Sorry, this should be an x here. Okay, sorry. Yeah. So we have this built-in parameter called blockdim.x. Okay. Now here, this .x is saying that this is the size of a block, right? The dimension of a block in the x direction. Okay. Right. So here, blockdim.x would be like 4, right? And then also, if you're in a 2D situation, you also need to know how large your thread block is in the y direction. So that's just blockdim.y. Okay, and if you have a 2D grid, right, you want to know how many thread blocks are in the x dimension. That's going to be again a built-in parameter here, griddim.x. Okay, and then in the y direction, griddim.y. Okay, and if you have a 3-dimensional thing, then you would have a griddim.z and then blockdim.z. Okay, so therefore, right, and then within a thread block, right. If you're in a 2D situation, right, then the thread has to have an ID both in the x and the y direction. Okay, so it's so a thread is going to have a block ID .x, which is a number between 0 to blockdim.x minus 1. Okay, the thread would also have a block ID .y, which is between 0 to this minus 1. Okay, and if you have a third dimension, it's also got a block ID .z. Okay. Oh, I'm sorry. A thread within a block. Okay, I'm sorry. A thread within a block, right? It's got a thread ID .x, which is a value between 0 to blockdim.x minus 1. Okay, and a thread ID .y in this direction. Okay, now this block ID .x is a number between 0 to grid dimension .x minus 1. Okay, that tells you which block you're in the x direction or in the y direction. Right. Okay, so all right, so now okay, map threads. Okay, so now all right, so now let's see like an example usage of this. Okay, so for example, suppose we're processing a matrix. Okay, then it's natural to use a 2D thread block, right? 2D grid and a 2D thread block. Okay, so then what we can do, suppose this matrix is width by width. Okay, so here width is 8, so it's 8 by 8. Right. Then you want to suppose you just want to cover this matrix with thread blocks. Okay, then we're going to make blocks of size. So each block is going to have size tile width by tile width. Okay, so for example here, right, we're going to have these 2 by 2 blocks. Okay, so then tile width is going to be 2, and then here you could also tile this matrix with bigger blocks with 4 by 4. Okay, right, and now if you use these 2 by 2 blocks, right, then you're going to have 4 blocks in the x and the y directions. Okay, And then if you use the tile width 4 here, right, then you need two blocks in the x and y directions. Okay. And now if you want to call a kernel, right, so previously we saw that you can call the kernel with like the 1D block and 1D grid. Okay. But what about like 2 or 3D, right? So then what you do is you define this thing called a dim grid, this data structure here. Okay, and this specifies how many blocks you want in the x and y directions, and also the z direction if you have it. Okay, but here we're two-dimensional, so our z direction just has one has a length of 1. Okay, and then you also specify how big each block is, right? So our blocks are tile width by tile width. Okay, and we don't have anything in the z direction. That's a 1 here, right? And now if you want to call the GPU kernel, right, you're going to call it with, this is going to tell you how many blocks you have, right? So here we have 2D blocks, right? And then this is telling you how big each block is. Okay, so now let's see how we can map different, once you start these threads, you need to map it onto the matrix. Right. So how do we associate different threads with different matrix elements? Right. Okay. So then we're going to map each thread to an element of this matrix P here. Okay. So the way we do this is if we're in this 4x4 thread blocks, right, and then we have 2x2 of these blocks, then we're going to take the block ID here, which is a number between 0 to 1. Okay, so the block ID in the y direction. So the block ID in the y direction, and then you multiply by the block dimension in the y direction, which is 4. Okay, because they're 4x4s, right? And then you add it to the thread ID, which is a number from 0 to 3. Okay, so that tells you which row you're in. Okay, so basically here, this block ID is between 0 to 1. Okay, right? And then here, this number is equal to 4 here, right? And this thread ID dot y is going to be a number from 0 to 3. Okay, right? So that tells you which row you're in. And then for the column, you're going to take your you're going to take which block you're in. So your block ID dot x. Okay, so you're either in block 0 or block 1 in the x direction, right? So this is also between 0 to 1. You multiply by the size of the x direction, which is 4 here, right? And then you add your thread ID dot x, which is like, suppose you're in this block, right? Then your thread ID is maybe a number between, it's going to be a number between 0 to 3. So like if you're here, right, then your thread ID dot x is going to be 2. Okay, so this is a number between 0 to 3 here. Okay, so then, so for example, you have thread 2.3, where is this one? Thread 2.3 in block 0.1. Okay, so 0.1 is going to be this block. 2.3, I suppose, is going to be this guy, right? So, okay, so then this thing here is going to be assigned to row, so we do this computation shown in blue, right? And then it's going to be assigned to this matrix element, the one in the 3rd row, 8th column. Sorry, this should be column here, right? And then this, and then this should be row here. Sorry about that. Okay, now you can check just with, so now notice that this is very similar to the 1D mapping thing, right? So it's basically the same formula, except for you apply it both in the x and the y directions. Okay, and so just as with the 1D mapping, we showed that every thread is mapped to a unique, to a different vector element, right? Then here you can show that every thread is going to be mapped to a different row and column in the matrix. Okay, also you can show that every matrix element has some thread being assigned to it. Okay, so now that we know how to map these 2D thread blocks and grids to a matrix, let's sort of use all this stuff to do an example of matrix multiplication. Okay, so here we're going to use 2D thread blocks and grids. Okay, so imagine that we have two matrices M and N. We want to multiply these, right? So these matrices are going to be width by width. Okay, right? So just this capital width here. Okay, right, and so the way we're going to do this is that for every output value, right? So our output is going to be P, right? For every one of these values, we're going to assign a thread. Okay, so if this width by width is like, if it's 8 by 8, we're going to have 64 threads. Okay, so each thread is responsible for computing just, that particular value. Okay, and so what it needs to do is it needs to just take a row from the M matrix and take a column from the M matrix and do the dot product. Yeah, and we're going to do all of these computations in parallel. We have width by width computations in parallel. Okay, so I'll just say a simple thing about how the matrices are stored in memory. So since CUDA is based on C, right, and C uses a row major format, then CUDA is also going to use a row major format. And so what that means is if you have a matrix like this, right, then we're going to store the first row followed by the second row and so on. Okay, and so therefore, if you're given a row and a column, right, then in order to, so we need to convert a row and a column into a 1D index in this array, which represents this matrix, right? And so the way to do that is if this matrix is width by width, okay, or actually, let's just say the width is the size in the x direction. Okay, then the index is just going to be which row you're in times the size of the width, right, plus the column. Okay, so for example, here our width is going to be 4, right? So if we're talking about something in the second row, right, this row over here, right, here row equals 2, right, and the column equals what, 1? Okay, right. Then this element here is actually going to be stored in index. If you do this computation, it's in index 9, right? So like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so now let's do this let's do this example. So I'm just going to show the kernel function here for the matrix multiplication. Okay, so we assume that M and N and P have already been pre-allocated. Okay, now first we're going to compute for each thread, we're going to figure out which item is it going to process. Okay, like for example, this thread, okay, which item of the output is it going to process, and that's given by this formula over here, which is just, where is it? It's this formula, okay? So again, this formula has these two features, right? We basically, this ensures that we compute the correct output. Okay. Right, and then once you figure out the row and the column, right, we need to check that we're not this is not out of bounds. Okay, so we have a width by width matrix. We need to make sure that the row and the column are both less than width, right? And then we're going to have this partial sum here. This p-value is basically we're just going to go we're going to go through these items one by one, right? The row and the column, right? And then you multiply the corresponding M and N elements. And then you keep adding this into this this partial sum over here. Okay, so so then now all we need to do is to figure out, so we're going to traverse this row of M, right, and then this column of N, and we need to figure out for each item, right, that we need to be processing, right, where is it stored in this M matrix and in this N matrix, okay. And now the formula for doing that, as I was showing on the previous page, is that you take the row that you're talking about times the width of the matrix plus the column. Okay, so for example, here, right, this element here is in row. This is the row and this is the column, right? And those are computed up here, right? So you take this row times the width of this matrix. Okay, so this here is width. Oops, it's kind of hard to write with this. Anyways, width. Okay, right. So you take the row times the width, and then our index here is k, right? So then k is going to go from 0 to width, right? So you add the k. Okay, right. So you use this formula, right? So the column is so here k is oops. right? So k is going to go from 0 up to width minus 1, right? Just like over here, okay? All right, so that's for the m, and then for the n, let's see. Okay, so for the n, since we're so k here is going in this direction, right? So then we need to take k times width, right? Because now k here is giving us a row, right? K here is giving us a column, right? This column or that, right? And then here, this is giving us a row, okay? It's giving us a row plus we're going to stay in this column, right? So therefore, the location of these n entries in this M matrix are given by these indices. All right, so then we multiply those guys, we add it to the p-value, and then after the end of this for loop, right, we have the correct p-value, and now we need to store it into the correct location in the output matrix, right? So now since we're in row and then column col, right? So then we're going to use that formula. Okay, yeah, so, all right, so now let's talk about this thing. So I've mentioned this several times, okay? So we have these two levels of threads, right? Blocks and grids, okay? Why do we have these two levels? Okay, so basically, imagine the alternative, okay? So on the GPU, we're gonna run millions of threads, potentially, okay? Or even billions of threads, okay? We could have up to billions of threads, okay? And I'll tell you why. Next lecture, I'll talk about why we want so many threads on the GPU. Okay. But anyways, we have many threads. Okay. Now, if we do not have a two-layer organization for these threads, okay, so then let's imagine a 1D organization. So then we somehow have to keep track of like millions of threads at the same time. Okay, if it's a 1D organization. Okay. Now, if it's a 2D organization, then what we have are maybe we have several thousand thread blocks. Okay. Now, each thread block might have a few hundred threads in it. Okay. So then what's going to happen is, all right. So let me first jump to, we need to look at how the how the GPU architecture is set up. Okay, so the GPU usually has a few thousand cores. Okay, the high-end GPUs have a few thousand, and the really cheap GPUs have a few hundred, but usually it's a few thousand cores. Okay, and as I said, they're grouped into these units called the streaming multiprocessors. Okay, and each streaming multiprocessor, so here we have a streaming multiprocessor. Okay, so this is kind of like a little multi-core processor in itself. Okay, so in fact, it's got all the features you want from a processor, from a multi-core processor. It's got like a cache here, right? It's got some scheduling, right? It's got some dispatch units and so on. It's got a bunch of registers, okay? Notice that it has like 32,000 registers over here, right? So I'll talk more about that later. And then it has some number of cores, okay? Usually a few dozen. So for example, something like 32 cores or 64 cores, okay? All right, yeah, so, and then all together, so this is one SM, and we might have a few dozen SMs all together on the GPU, which makes for a few thousand cores. Okay, now since altogether we have a few thousand cores, but we started several million threads, right, then obviously we cannot run all the threads simultaneously, right? Instead, we can only run a few thousand, however many cores we have, that's how many threads we can run simultaneously. Okay, so what happens is that we have the scheduler. So one name for it is called the gigathread engine. Okay, it packs like several hundred threads, maybe up to 1,000 threads, into a thread block. Okay, and it assigns the thread block to an SM. Okay, and the threads, as we saw, they have consecutive IDs. Okay, so if our thread block is size 256. The ID is like 0 to 255. Okay, and then the gigathreads engine might assign a few blocks to an SM. Okay, so maybe like depending on how big the blocks are, but it might assign let's say 2 thread blocks, each of size 512 to an SM. Okay, and now so therefore we've assigned 1,020. If it's 2 thread blocks of size 512, we've assigned 1,024 threads to an SM, right? but the SM, let's say, only has 64 cores. Okay, so you can't run all 1024 threads on the 64 cores, right? Okay, so then what's going to happen is that the 1024 threads that have been assigned to the thread block, right, they're further broken into these units of 32 threads called warps. Okay, so if you have 1024 threads and the warps are size 32, then we've broken them into 32 different warps. Okay, and if you have 64 processors, then you can run 2 warps on the SM simultaneously. Okay. Now, when you assign a block to an SM, so if the block has, let's say, 256 threads, then we know exactly how many resources that SM uses. Okay, so resource includes things like how many registers the threads use, right? Because after you write your program, right, the compiler can figure out how many registers each thread needs to use. Okay, so we know exactly how many registers each thread needs, and since we know the number of threads per thread block, we know the total number of registers that the thread block needs. Okay, so there are other types of resources like shared memory, which I'll talk about later, but we can also know a priori at compile time how much of these other resources the thread needs. Okay, so now since we know how much resources a thread block needs, right, then the GPU hardware is going to pre-allocate all these resources, okay, for the thread block. Okay, so if you need, let's say, 10,000 registers, okay, the GPU hardware is going to pre-allocate the 10,000 registers for this thread block, and it's going to keep those 10,000 registers for the thread block as long as that thread block is executing. Okay, maybe eventually the thread block finishes, and then after that, the GPU can reclaim those 10,000 registers. Okay, but as long as the thread block is executing, it's given this fixed amount of resources. Okay, now because it's given this fixed amount of resources, okay, so suppose you have a thread block of 256 threads, right? Okay, and then you need 10,000 registers. Okay, so that's basically about what? About 40 registers per thread, right? Okay, so the GPU is going to pre-allocate these 10,000 registers for you, so basically 40 registers per thread. And now, if you want to switch between 2 threads, okay, well, you've been pre-allocated this block of 10,000 registers. Okay, so suppose these are the suppose you have a group of, let's say, how do we make this computation easier? Let's say you have a group of 10 threads. Okay, okay, so then how do I write this? Okay, so yeah, so you have, let's say, 10 threads here, and they're going to use 400 registers. Okay, and now suppose you have another group of 10 threads, right? Oops. Okay, so they're going to use another 400 registers. Okay, right. Now all of these registers have been pre-allocated. Okay, so they're sort of they're just fixed in place on the GPU. Okay, now suppose you need to switch between this group of 10 threads to that group of 10 threads. Okay, then because these registers are just stored already on the GPU, you don't need to do any like switching. There's no cost to the switching because these 400 values are stored over here, and if I want to switch to the next 10 threads, I'll just read their register values, right? On a CPU, okay, compare this to the situation on a CPU where to switch between a thread, you would have to take all its register values, write them out to memory, okay, because you need to store those register values, right? So you store them in the memory, okay? Now you go to a new thread, you context switch to a new thread, right? And then you need to read the new thread's register values back from memory. So that's a huge cost, right? Because you need to go out to memory, okay? That's like, hundreds or thousands of cycles. So there's a big cost in CPUs for switching between threads. Whereas on the GPUs, right, because we've been pre-allocated all these resources, there's no cost, basically no cost at all to switching between one set of threads to another, because all you need to do is basically switch a pointer, right, that used to point to this block of registers, right? You just change this pointer to point over here. Okay, so it's very fast. Okay, so switching between threads is very fast. Okay. Yeah, so and this is made possible by the fact that you have many registers on the SM. Okay, so this was why you see over here, right? We have a very large number of registers. If you compare this to a CPU architecture, right, they have far fewer registers. Right here we have thousands of registers because the goal is to be able to run. The goal is to be able to run basically like, let's say, 1,000 threads, okay, per SM. Okay, so then if you want each each thread to have a reasonable number of registers, let's say 64 registers, okay, then you're going to need 64,000 registers for that SM. Okay, so now each SM has there's this gigathread scheduler is going to take the blocks and then put them onto SMs. Okay, now there's a second type of scheduler, which is like each SM has its own scheduler. Okay, so each SM, let's say it's been assigned 1,000 threads. Okay, so its own scheduler is going to switch between blocks of these threads, right? Because we said that you can't actually run all 1,000 threads simultaneously on the SM because maybe it only has, let's say, 32 cores. Okay, so you can only run 32 threads at a time. So you need to switch between groups of 32 threads. Okay, so the SM has a scheduler to do that. Okay, now eventually, so here, we have a block of threads over here, right? And they've been allocated these 10,000 registers. Okay, and they keep those 10,000 registers until this block completely finishes. Okay, when the block completely finishes, we're going to free all 10,000 registers. And now we can bring in the next thread block, right? And maybe that guy, next thread block needs, let's say, 20,000 registers. Okay, so we'll pre-allocate those 20,000 registers. And by doing the pre-allocation, we can make sure that we can switch between the threads very fast, right? We have a scheduler to switch between the threads of this second block, right? And then eventually, when the second block is finished, we're going to free up those 20,000 registers and bring in the third block, and so on. Okay, so the thing that's responsible for scheduling these new blocks is the gigathread engine. Okay, so that's how the GPU manages its threads. And so you see that by having this two-layer organization of like millions of threads, and then you break them into blocks of, let's say, 1,000 threads each, right? And then you schedule these 1,000 threads onto the SMs, and then you have a second layer of scheduling which switches between, let's say, blocks of 32 threads at a time, right? This makes it very organized and easy and efficient to manage a very large number of threads, millions of threads. Okay, yeah, so that's the basic reason for having these two layers of threads. Okay, so now, all right, so all right, so just a few more topics here. So next, I'm going to talk about synchronization on the GPU. Okay, so this is actually kind of a weakness of GPUs, which is it's hard to do synchronization between threads. Okay, in fact, what's going to happen is, so we have many thread blocks, and in fact, the thread blocks can execute in any order. Okay, so so now suppose let's consider an example. Okay, so if we have let's say we have a kernel with 8 thread blocks. Okay. Now, if you run this on a GPU with 2 SMs, okay, then one thing that can happen is that you run the first 2 thread blocks and then the next 2 and so on. Okay, so in that case, for example, thread 2 here, thread block 2 is running after 0. Okay. Now, however, you could also run this exact same kernel, okay, with 8 thread blocks. You could run this on a bigger GPU which has more SMs. Okay, so for example, the P100 has 56 SMs, right? If you get it like I don't know, like a P40, okay, maybe it's only got 28 SMs or something. Okay, so different GPUs have different numbers of SMs. And now if you have like, let's say 4 SMs, then what's going to happen is the first 4 thread blocks are going to run simultaneously, right? Because you can put 1 thread block per SM, at least, okay? So in that case, 0 and 2 are actually running concurrently. Right? You see that on the smaller device, 2 runs after 0, but on the bigger device, 0 and 2 run concurrently. Okay, so therefore your code, because when you write your kernel, right, you don't know what kind of GPU it's going to run on eventually, right? So you don't know whether 2 is going to run after 0 or concurrent with 0. So your code cannot depend on the order of the thread blocks, okay? Because potentially the thread blocks can execute in some arbitrary order, okay? So therefore, you cannot, your code cannot say that I'm going to wait for thread block 0 to finish some computation to produce some sort of output, and then because I need to use that output, okay? There cannot be that dependency, okay? So this is one example where it's hard to do synchronization on the GPU, okay? You cannot synchronize between blocks. Now, what if you really have a statement where you need to make sure that you have two statements, okay, where you need to make sure that the first statement finishes after this or finishes before the second statement starts? Okay, so the way to do this would be to put the two statements in different kernels. Okay, so so the kernels, right? The kernels are called by the CPU, and the kernels are always going to execute in sequential order. So you're going to do the first kernel. So let's say you put statement 1 in kernel 1, statement 2 in kernel 2, right? You're going to do the first kernel, it's going to finish, and then the CPU is going to call the second kernel. So that way statement 2 definitely comes after statement 1, and if statement 1, for example, produces a value that statement 2 needs, right, then you can correctly transfer the value from 1 to 2. Okay, however, it's rather expensive to launch a kernel. Okay, so this is a really poor way to do synchronization. So in fact, there are many types of synchronizations that are either hard to do or impossible to do on a GPU. Okay, so again, we said that GPUs are optimized for these data parallel tasks, right? So data parallel tasks usually don't have a lot of synchronization. Okay, so that's another reason why they work well on GPUs. Is because they don't require too much synchronization. Okay, so now we said that two different blocks cannot synchronize. However, you can do synchronization within a single block. Okay, so there's this function called _sync threads, which is basically like a barrier for all the threads within a block. Okay, so I'll talk more about that later, but within a block of, let's say, a few hundred threads, you can do synchronization. Okay, now we've been talking about these block sizes, right? So then, and right now I've just sort of chosen arbitrary values for these sizes, okay? But then what is the right value to choose, right? If you're allowed to choose an arbitrary value, why not just fix it at some value, right? And this actually depends on, so for example, if you're doing matrix multiplication, okay? Are we gonna use 8 by 8 blocks or 16 by 16 or what? Okay, so now there's actually some considerations that we have in choosing. So there is sort of a right way to choose a block size. Okay, and it's based on these considerations. So basically, our goal for all these considerations, okay, what we're trying to do is to maximize the number of threads that we can put onto an SM at each time point, and this is called occupancy. Okay, and I'll talk more about why you want to maximize occupancy in the next lecture. But that's our basic goal. And so how do you maximize occupancy? Well, you want to put as many threads as possible, but subject to a few constraints. Okay, so the first constraint is based on hardware constraints. Okay, so for example, there's a limit on how many threads you can put onto an SM, right? The GPU hardware puts a limit on how many threads can be assigned to an SM at a single time point. Okay, it also puts a limit on how many blocks can be assigned to an SM. Okay, and also there might be there is a limit, some sort of limit on how many threads per block. Okay, so now these limits are going to differ based on different GPUs. Okay, and then I'll tell you how to find these numbers later. But there definitely are these numbers, and so here I'm giving sort of ballpark figures for these numbers. Okay, so usually you're allowed to put maybe 1,000 or 2,000 threads onto an SM. Okay, and maybe it's something like 6 to 8 blocks. Okay, so you're not allowed to put like 10,000 threads onto an SM. Okay, there's no GPU that lets you do that, and I think most GPUs let you put at least 1,000 threads. Okay, so this 1,500 is kind of like an average number here. Okay, the blocks, right? It's something like 6 to 8. Okay, it's not going to be like 100 blocks, okay? And the threads per block, it's something like a few hundred. Okay, so then now, remember our goal is to run as many active threads as possible. Okay, so now let's look at it. So suppose you, so we're trying to decide between these 3 block sizes, right? So suppose you go with 8 by 8, right? Then you have 64 threads per block. Okay, now we can actually run 1500 threads on the SM. Okay, but if you only have 64 threads per block, you need to run 12 blocks to fully use up this SM. Okay, but remember you're only allowed 8 blocks. Okay, so if you're using 8 by 8 blocks, you cannot fully occupy this SM. Okay, now if you're using 16 by 16 blocks, you have 256 threads per block, and now 1536 divided by 256 is 6 blocks. So you know we can run 6 blocks, so this is fine. Okay, so this would run fine. That we can run 1500 threads with 16 by 16 blocks. Okay, and now the 32 by 32 blocks, right? Now that is going to be 1024 threads per block. And here we have a limit that we cannot run that many threads per block. Okay, so we cannot use this block size. So basically that's saying that we should use the 16 by 16 blocks. Okay. All right, so next we need to take into account the complexity of each thread. Okay, so remember that each SM has thousands of registers. Okay, but you know there's a limit. So maybe it's like let's say in our case it's going to be 16,000 registers. Okay, and suppose you have a bunch of threads that use 20 registers per thread. Okay, now if you have 16 by 16 thread blocks, right, you have 256 threads per block, and so they each use 20 registers. That's like 5,000 registers. Okay, so out of your so since you have only 16,000 registers available, right, then each block uses 5,000 registers, so you can run 3 blocks. 3 blocks is 3 times 256 is 768. Okay, and 768, remember that you could run 1500 threads, and you're only running a 768 here, so that's only half occupancy. Now somehow, suppose you could run 512 threads per block. Okay, right? Then each block would use 20 times 512 is 10,000 registers. Okay, so now you can only run 1 block. Okay, because if you run 2 blocks, you would need 20,000 registers, which you only have 16. Okay, so then now you can run only 1 block of 512 threads, and 512 over 1536, that's only 1/3 occupancy. Okay, right, so in this case, this also suggests that you would run 256 threads per block because you get higher occupancy. Okay, so in fact, you know, it's quite tedious to have to do these calculations yourself. So in fact, NVIDIA provides a tool that lets you do these computations, that sort of automatically lets you figure out your occupancy for the program that you're running, right? So this tool is going to figure out how many registers are used by each thread. It's going to look at how big your SMs are, and then it'll figure out your occupancy, okay? And if you have very low occupancy, then the suggestion is that you somehow modify your program so that you can sort of decrease this number here. Right? If you decrease this number, then you can run more threads in the SM. Okay, and the final consideration to choosing the right block size is that if you so even though GPUs are a SIMD architecture, sometimes and actually quite often in your code, the threads are going to do different amounts of work. Okay, so if you have a very large thread block, then it's quite likely that there's a substantial variation in the amount of work done by different threads. Okay, so that's sort of shown over here where you have n threads, and some of them, like thread 0 is doing a little bit of work, and thread n-2 is doing a lot of work. Okay, so there's a lot of variation. And in fact, the more threads you have, the more likely that this variation is quite large, right? So now the problem is that because of this variation, right, and the way the GPU works, so all of these threads belong to one thread block. And we said that this thread block is going to occupy an SM and then use up all the resources on that SM until the thread block finishes. Okay, so then let's say the thread block finishes at this time point over here. Okay, so we're occupying all of these resources, and yet we're not doing much productive work with this thread block because, you know, in all of this white region over here, right, these threads are not working. Okay, so in fact, what we want to do is to minimize this white region, right? This sort of idle region for the threads. Okay, and the way you can try to reduce that is the smaller your thread blocks are, right? The less variation there is between the different threads, right? And the less variation, the less waste there is. Okay, less. Yeah. So therefore, sometimes you don't want to have really huge blocks because there will be a lot of wasted idle time. Okay. Yeah. Okay, and there's a similar situation with barrier synchronization. Okay, so barrier synchronization. So GPUs have barrier synchronization. In fact, the sync threads operation is basically a barrier operation. Okay, so if this thread, if actually all the threads, if they do sync threads, then what that would mean is that the first thread to hit the barrier, okay, it's going to be waiting for all of the other threads to reach the barrier, right? And then it's only going to go on when all of the threads have reached that barrier. Okay. Now, if you have a very large thread block, then again, you might have a large variation in the runtime of different threads. So this you could have a bunch of threads just waiting at this barrier for the other threads to reach it. Okay. So that's more wasted cycles. Okay. So yeah. So you might want to reduce block size to reduce wasted cycles. Okay, so the final thing is that there are all these different hardware properties about the GPU, like how many SMs you have, how many threads you can put onto an SM, and so on, right? So now, of course, it depends on the GPU that you have, and you can't memorize all of these numbers. So therefore, you can there are functions for you to look up the numbers for your specific GPU, and so you can call these functions to get various properties about your GPU, right? And there are additional functions, and so if you look for the CUDA programming guide online, then that provides you much more complete information about these detailed functions. Okay, so then next time we're going to continue talking about GPUs. So see you guys next time.